Take a moment to feel the chair beneath you. You feel its weight and support. It feels solid and reliable. Yet, if we could peer into the atoms of that chair, we would find a different reality. The solid material is almost entirely empty space. The actual physical matter is like a few tiny dust motes drifting inside a vast cathedral. Welcome to Sleepy Mind Lab. Tonight, we will journey into this quiet void. We will travel from the subatomic spaces to the deep, silent gulfs between the stars. We will explore how everything we touch and everything we are is held together by forces acting across nothingness. Let your mind settle as we explore the elegant physics of the empty universe. We will uncover the quiet dance of fields and forces that create the illusion of solidity. The gold foil discovery. Let us travel back in time to a chilly laboratory in Manchester during the year 1909. The air is damp and the room is filled with the faint hum of early scientific instruments. A physicist named Ernest Rutherford, along with his colleagues, is about to perform an experiment that will change how we understand the very fabric of our reality. At the time, scientists believed that atoms were solid, soft spheres, like a sweet plum pudding, with tiny negative charges scattered throughout a positive soup. It was a comforting, solid picture of the universe. Everything around us was thought to be packed tight, filled with substance. Rutherford wanted to test this idea. He set up a delicate experiment, using a tiny source of radiation to shoot microscopic particles at an extremely thin sheet of gold foil. This gold leaf was so thin that it was only a few hundred atoms thick. He expected these heavy, fast-moving particles to pass right through the soft atomic pudding with almost no resistance, perhaps bending only a tiny fraction of a degree. It was like firing bullets at a thin paper wall. For days, the researchers sat in the darkness, letting their eyes adjust to the dim light of a detector screen. Every time a particle hit the screen, it created a tiny flash of light. They watched, and they counted. Most of the particles did exactly what they expected. They zipped straight through the gold foil, flying onward in a direct line, as if there was absolutely nothing in their way. The gold sheet, which looked solid to the human eye, seemed to present no barrier at all to these tiny projectiles. But then, something completely unexpected happened. A tiny fraction of the particles did not pass through. Some of them were deflected at sharp angles, and, even more strange, about 1 in every 8,000 particles bounced straight back, reversing direction entirely. Rutherford later said, "It was as if you had fired a 15-inch artillery shell at a piece of tissue paper, and it bounced back and hit you." This simple observation shattered the old way of thinking. The solid plum pudding model of matter was gone in an instant. If a heavy projectile bounces straight back, it must have hit something extremely dense, extremely heavy, and extremely small. Rutherford realized that the atom is not a uniform, solid ball of pudding. Instead, almost all the mass of the atom is concentrated in a tiny, dense core at the very center, which we now call the nucleus. The rest of the atom, the vast space surrounding this tiny core, is almost completely empty. The particles that sailed straight through the gold foil did so because they encountered nothing but void. They passed through the wide, empty spaces between the tiny nuclei. This discovery changed our relationship with the material world. It meant that the chair you are sitting on, the floor beneath your feet, and the very air you breathe are not solid structures. They are mostly empty space, held together by invisible forces. The solid world we touch and feel is a ghost, a phantom created by a few tiny points of matter spinning in a vast, dark emptiness. But how vast is this emptiness inside a single atom compared to the things we can actually see? The scale of hydrogen. Let us begin by stepping onto the green grass of a massive sports stadium. Imagine walking right out to the center, to the 50-yard line, and placing a single glass marble directly on the turf. This marble is small, cool to the touch, and still. In our cosmic scale model, this marble represents the proton, the heavy heart of a single hydrogen atom. It holds almost all the mass of the atom, sitting quietly in the very center of its world. Now, we must search for the partner to this proton, the single electron that balances the system. To find it, we have to travel far away from the 50-yard line. We must climb up the stairs, past the lower decks, past the luxury suites, and go all the way to the very top row of the nosebleed seats, high up under the roof. Up there, floating in the air, is a tiny speck of dust. That speck of dust represents the electron. If we stand back and contemplate this entire space, the scale becomes clear. The distance from the marble on the grass to that speck of dust in the highest seats is vast. And in the space between them, there is nothing. No concrete, no steel, no seats, and no air. In a real hydrogen atom, that entire stadium is completely empty. There is only the marble in the center and the dust speck at the edge. The rest of the stadium is a quiet, hollow gap. If we could enlarge a hydrogen atom so that its nucleus became the size of a marble, the outer boundary of the atom would easily cover the entire stadium. If you were to walk from the marble to the electron, you would walk through a massive expanse of silence. The electron does not even orbit in a neat circle like a planet. Instead, it exists as a sort of whisper, a cloud of probability existing in many places at once, somewhere high up in those distant stands. The vastness of this inner space is difficult for our minds to grasp. We are used to solid things, like wooden chairs and stone walls. Yet, the building blocks of everything we touch are structured like these giant hollow arenas. Think about the sheer proportion of this arrangement. The nucleus is tiny, yet it holds more than 99.9% of the mass of the atom. The electron is light, holding almost no mass at all. Yet its influence defines the outer boundary of the atom. The boundary of the atom is far from a hard wall. It is simply the limit of where the electron might be found. The rest of the space remains empty of smaller particles or hidden structures, existing instead as a pure, silent void. When we hold a cup of water, we are holding billions of these tiny stadiums. Every drop of water, every cell in our hands, is made of these vast chambers of quiet space. We feel a sense of solidity when we touch a table because the outer edges of these stadiums repel each other, rather than because they are packed tight with matter. The reality of a hydrogen atom is that it is a lonely marble and a distant speck of dust, separated by a silent gulf. It is a quiet reminder that the foundation of our physical world is built on a scale of vast, open emptiness. Our universe is built from these vast, quiet distances where almost nothing exists, rather than solid blocks. The strong nuclear glue. Let us travel deeper into this quiet landscape, past the outer cloud of electrons, right into the very center of the atom. Here lies the nucleus, the dense core of all matter. We often imagine this core as a cluster of neat, solid marbles packed tightly together. But if we could shrink down and examine a single proton within this nucleus, we would discover that it is not a solid object at all. Instead, we would observe a wild, energetic storm. Inside this tiny domain, three fundamental particles called quarks are constantly moving. They do not sit still, and they never rest. They dance and swirl in a space that is otherwise completely empty. We can think of them as three small leaves caught in a powerful, localized wind blowing in circles. What keeps these three quarks from flying away from each other? They are held together by a force that we call the strong force. This force is carried by even smaller messengers called gluons. Gluons act like an extremely strong, sticky glue, flying back and forth between the quarks at the speed of light. They are constantly being exchanged, holding the quarks in a tight, permanent embrace. This constant, rapid exchange of gluons requires an immense amount of energy. And here is one of the most surprising secrets of the subatomic world. Almost all the weight of the proton does not come from the quarks themselves. The quarks are actually extremely light, almost weightless. Instead, the mass is created by the pure energy of the gluons rushing back and forth. The energy of this motion is so intense that it behaves like solid mass. When we hold a heavy object in our hands, we are actually feeling the weight of this trapped, vibrating energy. Without this strong force, the nucleus of every atom in the universe would instantly tear itself apart. The positive electric charges of the protons would push them away from each other with violent speed. The entire material world, from the water in a glass to the ground beneath our feet, would dissolve in a single moment into a cloud of scattered particles. So even at the deepest level of matter, what we perceive as solid weight is actually the trapped energy of a storm, holding together particles inside a vast empty space. It is a delicate balance of forces, keeping the void from tearing the universe apart. Every solid thing we touch is a whisper of energy holding the emptiness together, a beautiful shield against the void. The force of touch. Rest your hand on the table in front of you. Or, better yet, hover your palm just a fraction of a millimeter above the cool wood. You feel the presence of the surface. You feel the pressure, the texture, the solid boundary where you end, and the table begins. We spend our entire lives believing that we are making physical contact with the world around us. We believe that when we hold a cup of warm tea, press a key on a keyboard, or hug a loved one, our matter is pressing against their matter. But if we zoom down to the scale of the subatomic, the story changes completely. You have never actually touched anything in your entire life. You have never touched the hand of a friend, the soft fur of a cat, or the soil of the earth beneath your feet. To understand why, we have to look at the outer edges of the atoms that make up your skin and the wood of the table. Every atom is surrounded by a cloud of negatively charged electrons. These electrons are not solid particles like tiny marbles. They are spread out in waves of electrical charge, filling the space around the central nucleus. When you bring your hand down toward the table, the electrons in your fingertips begin to get close to the electrons in the wood. They do not want to mingle. They do not want to overlap. Think about what happens when you try to push two magnets together. If you align the same poles of two magnets, you feel a strange resistance. The closer they get, the stronger the pushback. No matter how hard you squeeze, they want to slide away from each other. They do not want to meet. A similar thing is happening at the boundary of your hand and the table. The negative charge of your electrons repels the negative charge of the table's electrons with immense strength. They push away from each other with a force that grows exponentially as the distance shrinks. As you press down, this repulsive force grows stronger. Eventually, the force becomes so powerful that it stops your hand from moving any further. This resistance is what your brain interprets as touch. You feel the hardness of the wood, but you are actually feeling the electromagnetic field pushing back against your own field. You are hovering on a microscopic cushion of force, suspended a tiny fraction of a millimeter above the surface. You are floating. Every time you sit in a chair, you are levitating above the seat. When you walk, your feet are riding on waves of repelling force, never truly making contact with the ground. The physical contact we experience is a sensory translation of electromagnetic repulsion occurring at the atomic scale. The feeling of solidity is an illusion created by your nervous system to make sense of this invisible struggle. The universe keeps us at a distance ensuring that we remain forever separated from the objects we believe we hold. We are forever separated by a tiny, unbridgeable space. If you could turn off this electromagnetic force for even a single second, the illusion of solidity would vanish. Your hand would slide right through the table, and you would fall through the floor toward the center of the Earth. We are held together and held apart by this delicate dance of fields. But why do these orbiting electrons not just collapse into the nucleus, closing the empty gap? The Pauli exclusion principle. Let us pause for a moment and consider a strange riddle. If the atoms that make up your body, your chair, and the walls around you are almost entirely empty space, why do you not simply slip through the floor? Why does your hand not pass right through a wooden table when you rest it there? It feels so solid, so real. Yet we know there is almost nothing physical occupying that space. The answer lies not in a physical barrier of hard, tiny spheres, but in a fundamental rule of the universe. It is a cosmic law of identity, a rule that dictates how the building blocks of matter must behave. We call this the Pauli exclusion principle, and it is perhaps one of the most quiet, yet powerful forces shaping our daily experience of reality. To understand this, we must examine electrons. These tiny particles do not orbit the center of an atom like planets around a sun. Instead, they exist in a cloud of possibilities, defined by a specific set of numbers that tell us their exact state. These numbers describe their energy, their shape, and their orientation. In a way, these numbers are like a unique address in the quantum world. The rule is simple. No two electrons in the same atom can share the exact same address. They cannot occupy the same state at the same time. If one electron is already in a specific state, any other electron must find a different one. It is a strict rule of individuality. Imagine a grand theater where every seat has a specific row and number. Once a guest sits in a seat, no one else can sit in that exact spot. They must move to the next row or the next level. As more and more guests arrive, they are forced to occupy seats further and further from the stage. This is exactly what happens inside an atom. The electrons cannot pile up at the bottom in the lowest energy state. They are forced to build outward, occupying higher and higher levels of energy, spreading out and filling the space. This simple requirement for uniqueness is what gives atoms their volume. Without this rule, every electron in every atom would collapse down to the very center, right next to the nucleus. Matter would shrink to a tiny fraction of its size. Your body, the Earth, and everything we know would instantly collapse into a point so small you could barely see it. This rule creates a structural resistance that holds the empty space open. When you press your hand against a table, the electrons in your hand are trying to occupy the same quantum states as the electrons in the wood. But the universe forbids it. The electrons resist being forced into the same state. This resistance is not a physical wall, but a mathematical boundary. It is a beautiful realization. The solid feel of the world is not caused by solid matter at all. It is the result of a mathematical law of uniqueness, a rule that forces particles to keep their distance and respect each other's identity. We live in a universe held open by a simple rule of math, a law that keeps the void from collapsing in on itself. The illusion of solidity. Let us take a moment to notice what is happening right now. If you are typing on a keyboard, or perhaps resting your fingers on the surface of a desk, you feel a distinct sensation of resistance. The keys push back against your fingertips with a quiet, reassuring pressure. The wood of the desk feels firm, stable, and undeniably solid beneath your palms. We move through our daily lives relying on this hardness without ever questioning it. We sit on chairs, walk on pavement, and hold cups of warm tea, never doubting that these things are completely filled with matter. It seems obvious that the physical world is made of hard, solid objects that occupy space in a permanent way. But what is actually happening at the boundary where your finger meets the keyboard? As your hand approaches the plastic key, the microscopic fields of the atoms in your skin come close to the fields of the atoms in the plastic. They never actually make contact. There is no physical touching in the way we usually imagine it. Instead, as these fields push against each other, the resistance triggers tiny specialized nerve endings in your skin. These receptors convert that physical resistance into a tiny, rapid burst of electricity. The physical sensation of pressure is instantly converted into a message of electrical pulses. This electrical signal travels up your arm, moving through your nervous system, and enters the quiet dark of your brain. Once the signal arrives, your mind receives this information and translates it. Your brain tells you that you are touching something hard, flat, and real. The feeling of solidity is not a property of the desk itself, but rather a neurological translation. It is a sensory map created inside your head, a simulation of hardness designed to help us interact with our surroundings, rather than a fundamental property of the universe. If we could somehow strip away this sensory translation, we would find that the universe is made of silent, invisible forces holding each other at a distance. The solid desk is actually a vast network of empty space where forces interact. Your brain acts like a translator, turning the quiet, empty dance of fields into the rich, textured experience of a physical world. Every texture you feel, from the softness of a blanket to the cold hardness of metal, is just your brain interpreting how fields repel one another. We live in a reality where emptiness is the rule, and solidity is a beautiful, necessary illusion created by our own minds to help us navigate the quiet void. The void inside the nucleus. We have journeyed deep into the atom, past the vast orbits of electrons, until we reached the tiny, dense core. Now we must go even deeper. Let us travel deep into a single proton, one of the building blocks that we think of as solid matter. We might expect to find a hard, solid ball, a tiny marble of pure substance. Instead, as we cross the threshold of the proton, we find ourselves entering another vast, quiet cathedral of empty space. This is far from a simple void. It is a region where the rules of the everyday world no longer apply. Deep inside this tiny boundary, we can detect three tiny points. These are the quarks, the fundamental pieces that give the proton its identity. Yet, if we try to measure them, we discover something strange. These 3 points take up almost none of the space inside. They are like three tiny gnats flying around inside a sports stadium. The actual physical volume of the quarks is practically zero. They account for less than 1% of the space they occupy. This leaves us with a question. If the quarks are almost nothing, what fills the rest of the proton? The space between them is not empty in the way we usually think of a void. It is a turbulent, shifting sea of energy. It is filled with fluctuating fields that constantly ripple and churn. Particles of force flash in and out of existence, appearing for a tiny fraction of a second before vanishing back into the vacuum. This constant motion creates the illusion of solidity. The mass of the proton, the weight that gives you and me our substance, is entirely separate from solid matter. It comes from the kinetic energy of this wild, invisible dance. In a very real sense, weight is just confined energy. As we observe closer, we realize that the idea of a solid object dissolves completely. There is no hard surface to touch, no boundary you could tap with a finger. There is only a region of space where forces become intense. If we try to find a solid bottom to the scale of matter, we find that the concept itself slips away. We are made of atoms, which are made of protons, which are made of quarks. But at every level we descend, the solidity disappears, replaced by empty space and energy fields. We are, at our deepest level, built from the quiet activity of the vacuum. The structure of the universe is built on the silent music of fields vibrating in the dark, rather than on solid bricks. We are held together by the relationships between empty spaces, rather than by hard pieces of matter. Quarks and point particles. How small is a quark if we try to measure its physical surface? If we were to take a hypothetical magnifying glass of infinite power and zoom in on a proton, past the buzzing clouds of energy, down to the 3 quarks residing at the center, what would we actually detect? We would find ourselves searching for a boundary that does not exist. In our everyday world, everything has an edge. A grain of sand has a surface. A cell has a wall. Even a single atom has a rough boundary defined by its electron cloud. But when we examine the most fundamental building blocks of our universe, the particles that cannot be divided any further, this rule of surfaces completely breaks down. According to the standard model of physics, quarks and electrons have no physical dimensions at all. They do not have a width. They do not have a height. They do not have a depth. They are what physicists call point particles. This is a concept that is difficult for our minds to accept, because we live in a world where everything occupies some amount of space. We are used to thinking of particles as tiny billiard balls, extremely small spheres of solid matter. But a sphere has a radius. A sphere has a volume. A quark has neither. If you try to measure the volume of an electron or a quark, you will find that the answer is 0. They are infinitely small coordinates in space. They are mathematical points, locations where properties like mass and electric charge exist, but without any physical body to hold them. Imagine a point in geometry. It tells you where something is, but it has no length or width of its own. That is what a quark is. It is a location of property, a coordinate of existence. Think about what this implies for the nature of everything around you. The chair you are sitting on, the objects surrounding you, the very body you inhabit, are all made of atoms. And those atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. If quarks and electrons occupy 0 volume, then the fundamental building blocks of all matter occupy no physical space. The solid objects we touch are constructed entirely from components that have no physical size. This realization brings a strange, quiet stillness to our understanding of reality. We are accustomed to thinking of emptiness as the space between things. We imagine a room is empty when we take the furniture out. We imagine space is empty between the stars. But this goes much deeper. The very things we use to fill the emptiness are, at their core, made of nothingness themselves. The particles are just points, mathematical dots on the grid of the universe. They have no volume to call their own, no inner world to hide inside. They simply mark the places where forces gather. When you touch a table, you feel resistance. You feel a solid barrier. Yet, that barrier is made of points that have no width or breadth. The sensation of solidity is a force field pushing against another force field, a dance of mathematical coordinates repelling each other across a void. The physical stuff is not really there in the way we think it is. If we were to strip away the fields and the forces and only consider the actual volume occupied by the matter itself, the entire universe would disappear. The building blocks of reality do not take up any room. They are simply locations where the universe has decided to manifest properties. If the particles themselves occupy no space, does that mean the space between them is completely empty? The quantum vacuum. Imagine a simple box. We remove every single thing from the inside of it. We pump out all of the air, every atom of gas, and every stray speck of dust. We cool the box down to absolute 0 so there is no heat energy left inside. We shield it perfectly from any passing light, radio waves, or radiation from the outside world. In our everyday experience, we would say, the box is now completely empty. We would call it a perfect void, a quiet place of absolute nothingness. But if we could shrink down and examine this space on the smallest possible scale, we would find that the void is not quiet at all. It is actually humming with activity. This silent, dark space is boiling with energy. In the world of quantum physics, a true vacuum does not exist. Space is never empty. Instead, it is filled with invisible fields that are constantly moving, stretching across the entire cosmos. These fields are like an invisible fabric that covers every corner of the universe. We can think of them as quiet, resting layers of energy. When a field gets excited, it produces a particle. A particle of light is just a ripple in the electromagnetic field. In a vacuum, we have removed all the ripples, but the underlying fields are still there. How can a space with nothing in it still have energy? The answer lies in a fundamental rule of nature called the uncertainty principle. This rule tells us that at the quantum scale, we cannot know everything about a physical system with perfect precision. There is always a tiny, unavoidable amount of fuzziness in the universe. Because of this fuzziness, the amount of energy in a tiny patch of space cannot stay at exactly zero. It fluctuates up and down, constantly changing. These fluctuations are like tiny waves on a calm ocean. Even when the water appears still from far away, if we examine it closely, the surface is always moving. In the vacuum of space, these energy waves are constantly rising and falling. During these brief moments of fluctuation, the vacuum borrows energy from the universe. With this borrowed energy, particles are created out of nothing. They do not appear alone. They always come in pairs. One is a normal particle, and the other is its antimatter partner. They pop into existence together, like twins born from the vacuum. But this borrowed energy must be paid back almost instantly. The particle and its antimatter partner search for each other. As soon as they meet, they collide and destroy each other. They dissolve back into the energy of the field, returning what they borrowed. This entire process happens in a fraction of a second, so fast that we cannot detect them directly. Scientists call them virtual particles because they exist only on borrowed time. As a result, the empty space all around us, and even the space inside our own bodies, is constantly breathing. Millions of these tiny particles are popping into existence and disappearing every single second. It is a quiet, continuous dance that never stops, happening in the palm of your hand and in the cold spaces between the stars. If we think about the cosmos this way, our idea of nothingness changes. Space is not a passive stage where things happen. Space itself is active. The vacuum is a lively sea of potential. It is a place where matter is constantly trying to exist, even if only for a brief moment. Even if we traveled to the deepest, darkest area between the galaxies, millions of light years away from any star, we would still find this active sea. True nothingness is impossible because the fields of the universe are always awake. They are always humming. The void is not empty. It is full of life that is waiting to happen. The Casimir Effect. Consider two tiny flat plates made of metal. We place them in a dark chamber, completely emptied of air and chilled to the coldest temperature possible. We bring these plates so close together that the distance between them is smaller than the width of a single human hair. They are not connected to any battery. They carry no electrical charge. There is no magnet nearby. By all traditional rules of physics, they should just sit there, perfectly still, ignoring each other. Without any outside force, they begin to move. A mysterious, invisible hand seems to gently push them toward one another until they cling together. This is far from magic. It is a physical demonstration of the restless energy that fills every corner of empty space. To understand why this happens, we can think of the ocean. Suppose two large ships are parked side by side in the open sea. Out on the open water, waves of all different sizes roll in from every direction, tossing the ships about. But in the narrow gap between the two hulls, only small, short ripples can fit. The long, powerful swells are too big to squeeze into that tight space. Because there are more waves, and larger waves, crashing against the outside of the ships than there are bouncing between them, the water pushes the two vessels toward each other. The water outside is more active, driving the ships together. A very similar thing happens to our metal plates in the dark, empty chamber. Even though the air is gone, the space is still alive with invisible, shifting waves of energy. These waves fluctuate constantly, appearing and disappearing in the void. In the wide open space outside the plates, waves of every possible size can exist. They ripple freely. But in the tiny gap between the two plates, only the shortest waves can fit. The longer waves are simply squeezed out because they cannot find room to vibrate. This creates a difference in pressure. The quiet storm of energy waves on the outside is stronger than the waves trapped on the inside. The outside waves press inward, nudging the plates together. This gentle squeeze is a measurable physical force. It is a quiet whisper from the empty space itself, proving that even when we remove everything we can, the void is never truly empty. It is active, dynamic, and strong enough to move solid matter. We can measure this force in modern laboratories, showing that empty space exerts a real physical push on our world. The Higgs Field. Imagine stepping into a swimming pool, but instead of water, the pool is filled with thick, warm molasses. Every time you try to take a step, you have to push against a heavy, sticky resistance. Your legs feel extremely heavy, and every movement requires effort. If you try to run, you are met with an even stronger drag that holds you back. In a simple way, this is very similar to how the universe gives mass to the building blocks of reality. We tend to think of mass as something solid, an inherent heaviness that particles simply possess from the moment they are created. We often think that an electron or a quark is heavy because it is made of some dense, microscopic stuff. But the deeper we look into the nature of empty space, the more we realize that mass is not a permanent quality of matter at all. Instead, mass is a continuous interaction, a constant drag force generated by an invisible presence that fills the entire cosmos. This invisible presence is known as the Higgs Field. It is not like a cloud or a gas that occupies certain regions of space while leaving other areas empty. It is a fundamental field that permeates every single cubic centimeter of the universe. Even in the deepest, darkest void between galaxies, far away from any stars or planets, where there seems to be absolutely nothing at all, the Higgs field is there. It is a quiet, silent background that never turns off, stretching from one edge of the cosmos to the other. Every particle in the universe is constantly moving through this field. Some particles, like the photon, which is the basic unit of light, pass through the Higgs field without feeling any resistance at all. It is as if the molasses does not exist for them. Because they experience no drag, they are able to travel at the absolute speed limit of the cosmos, which is the speed of light. They have no mass, and they can never slow down or rest. They are forever bound to race through the cosmos. Other particles, however, are not so lucky. As they move through the vacuum, they interact with the Higgs field, catching on it and feeling a constant, subtle drag. This interaction slows them down, preventing them from ever reaching the speed of light. We perceive this sluggishness, this resistance to movement, as mass. When you lift a heavy object, like a stone or a book, you are not actually feeling the weight of solid matter. You are feeling the resistance of billions of tiny particles struggling to move through the sticky background of the universe. If we could somehow turn off the Higgs field, even for a single second, the entire structure of physical reality would instantly dissolve. Without this cosmic drag, every single particle that makes up your body, the air you breathe, and the ground beneath your feet would lose its mass. Every electron would suddenly become weightless and fly apart at the speed of light. Atoms would disintegrate in an instant, unable to hold themselves together. The stars and planets would vanish, leaving behind nothing but a chaotic, blinding flash of light, zipping through an endless void. We owe our entire physical existence to this quiet, invisible friction. It is the very thing that allows the emptiness of space to crystallize into the solid, stable world we touch and feel every day. Without the Higgs field, there would be no planets, no chemistry, and no life. Only empty space and light. Cosmic scale and solar space. We often see maps of our solar system printed in school textbooks, where the planets sit neatly next to one another like colorful marbles on a wooden table. But these drawings are highly misleading because they have to fit onto a single page. If we were to draw the solar system to its actual scale, we would find a map of almost nothing. The reality of our cosmic neighborhood is one of extreme isolation. A quiet expanse where objects are separated by distances that challenge our everyday understanding. To understand how vast this empty space really is, we can shrink everything down to a size we can easily hold in our hands. Imagine the sun is the size of a grapefruit sitting on your kitchen table. In this tiny universe, our home planet, the Earth, is not a large blue marble nearby. It is a single grain of sand located about 50 feet away, perhaps out in your driveway or sitting in your neighbor's garden. Between that grapefruit and that grain of sand, there is almost nothing at all, just silent, empty air. Now, let us venture further out into the dark. Jupiter, the largest planet in our solar system, would be the size of a cherry. But to place it at the correct distance from our grapefruit sun, we would have to walk 2 blocks down the street. Saturn, another giant world, would be the size of a slightly smaller cherry, located 4 blocks away. By the time we reach the outer edges of this planetary neighborhood to find Pluto, we would find a tiny speck of dust sitting more than 1 mile away from our kitchen table. Between these few scattered objects, there is only a cold, quiet vacuum. It is easy to think of outer space as being filled with swirling dust clouds, floating asteroids, and colorful gas, but the reality is much more sparse. The solar system is a vast desert of empty space, where the oases of matter are so small and so far apart that they barely register against the dark background. The dust and rocks we imagine filling the void are actually very rare, leaving only a pure vacuum. When we contemplate the night sky, we confront a window of profound silence. The planets are lonely wanderers rather than neighbors sharing a yard, separated by vast oceans of nothingness. The material that makes up all the planets, the moons, and the asteroids is only a tiny fraction of a percent of the total volume of our solar system. The rest is just empty space, stretching out in every direction, silent and dark. We live on a tiny speck, suspended in an ocean of emptiness. The cold Oort cloud. Imagine drifting trillions of miles away from the warmth of the sun, deep into the outermost edges of our solar system. Here, in the dark region known as the Oort cloud, the familiar worlds of rock and gas are far behind. You are floating in a silent, freezing shadowland. In this place, icy rocks and frozen comets drift through the dark, but they do not crowd together. Instead, these quiet remnants sit light hours apart from one another. If you stood on one of these icy blocks, The next nearest traveler would be so distant that it would be completely invisible, lost in the shadows. There is no warmth here. The sun, which felt so large and hot on Earth, has shrunk to a tiny pinpoint of light. It looks like just another bright star in the dark sky, offering no comfort and no heat. The cold is deep, and the silence is absolute. This emptiness is ancient, remaining unchanged since the very birth of our solar system billions of years ago. It is a quiet, lonely frontier where gravity barely holds on, and the gaps between the frozen stones are so vast that they make the rest of the solar system feel crowded. You are surrounded by a quiet void, a place where almost nothing ever happens, and where the distance between things is the only real presence. In this quiet place, you can feel how thin the fabric of our solar system really is, with each icy mountain drifting alone in the dark, separated by vast oceans of nothing. Here, at the very boundary of our home in the galaxy, emptiness is the canvas itself, and the icy rocks are merely tiny specks of dust lost in the dark. The interstellar medium. If you were to take a giant box, say 1 meter wide, 1 meter long, and 1 meter tall, and scoop up a random piece of the deep space between the stars, what would you find inside? If you closed the lid and examined the contents, you could expect to find some dust, or maybe some cosmic debris. In reality, you would find almost nothing. Inside that entire cubic meter of space, there would be only a handful of lonely hydrogen atoms, drifting slowly, and a few stray particles of light. To understand how empty this is, compare this box to a single breath of air on Earth. Every time you inhale, you draw in about 26 billion trillion molecules of nitrogen, oxygen, and other gases. The density of our atmosphere is so high that these molecules constantly bump into each other trillions of times every second. But out in the dark lanes between the stars, a single atom can travel for years, even decades, without ever hitting another atom. The distance between them is vast. It is a vacuum far more perfect than any laboratory on Earth could ever hope to create. A quiet void stretching across light years. We tend to think of space as a crowded place filled with glowing nebulae, spinning planets, and bright stars. Yet the space between those stars is a silent desert of cold, lonely particles, separated by distances that are difficult to comprehend. The stars are mere islands of matter in an ocean of silence. But what happens when these vast, empty stellar neighborhoods collide with one another? Galaxies passing through. In about 4 billion years, our home galaxy, the Milky Way, will meet its nearest large neighbor, the Andromeda Galaxy. They are currently rushing toward each other at immense speeds, drawn by their mutual gravitational pull. When we think of a collision between two massive objects, we usually picture a violent crash. We imagine rocks breaking, metal bending, and debris flying in all directions. But a cosmic collision of two galaxies is nothing like that. It is a slow, ghostly dance where almost nothing actually touches. To understand why this happens, we have to look at the scale of the empty space between the stars. Imagine our sun was the size of a single ping-pong ball sitting in New York City. The nearest star to our sun, Proxima Centauri, would be another ping-pong ball located in Atlanta, Georgia. Between those two tiny balls, there is nothing but empty air. If you threw a handful of ping-pong balls from New York toward Atlanta, the chance of any two of them hitting each other is practically zero. This is the reality of our galaxy. The Milky Way contains several hundred billion stars, and Andromeda contains perhaps 1 trillion. Yet, they are so widely separated that they are like tiny specks of dust floating in a giant cathedral. When the two galaxies merge, they will slide right through each other. The stars will glide past one another, guided only by the gentle pull of gravity. They will pull and stretch each other into new shapes, creating long, beautiful tails of stars. But the individual suns will almost certainly never collide. Imagine two swarms of bees meeting in the air. Instead of crashing, they simply mingle, their paths crossing, without a single insect bumping into another. A resident on a planet orbiting one of these stars would look up at a night sky slowly changing over millions of years. They would watch the stars of the other galaxy drift past, bright and close, yet completely harmless. The sky would grow crowded with new light, but the quiet of their own solar system would remain undisturbed. Even the supermassive black holes at the centers of these two galaxies will not immediately collide. They will simply loop around each other in a wide orbit, slowly spiraling inward over millions of years, while the rest of the stars continue their peaceful drift. The entire event is less of a crash and more of a quiet rearrangement, a new pattern drawn in the dark. This cosmic meeting reveals that even the most massive structures in the universe are made almost entirely of nothing. Galaxies look like solid, glowing spirals in photographs, but they are mostly vast, quiet voids. They are elegant structures of light and gravity, drifting through the darkness, passing through one another like ghosts in the night, leaving no scars behind. The Boots Void. Let us take a journey far beyond the familiar clusters of stars we call home. Imagine traveling to a place where the darkness is so profound that it feels almost physical. This is a pocket of space 330 million light-years across. Scientists call it the Boots Void, but you can think of it as a vast, silent desert in the cosmos. It is one of the largest empty spaces we have ever found. To understand how empty this place is, we can compare it to our own neighborhood in space. From our position in the universe, we detect thousands of galaxies scattered across space, like bright cities on a map. But if our own galaxy, the Milky Way, had been born inside the center of the Boots Void, our experience would be completely different. We would find ourselves in a deep, endless blackness. We would not have known that other galaxies even existed until the 20th century, when our telescopes became powerful enough to reach across millions of light-years of nothingness to the very edge of the void. If we searched the sky from a planet in that darkness, we would have believed we were entirely alone in the cosmos. For a long time, we believed that space was evenly filled with stars and galaxies, like a gentle mist. Instead, the universe is more like a giant sponge, full of massive holes. The Boots Void is the largest of these holes. In a region of space this size, we would normally expect to find thousands of galaxies. Yet, in this entire expanse, we have only found about 60 of them. These lonely galaxies are separated by distances so vast that they can never interact, drifting in isolation like single ships on a dark ocean. If you were to travel from one to the next, the journey would take hundreds of millions of years of traveling through absolute nothingness. This emptiness presents a difficult puzzle for scientists. According to our current understanding of the cosmos, the universe started as a hot, dense soup. Over billions of years, gravity slowly pulled matter together to form stars and galaxies. But the sheer size of this void challenges our ideas about how matter clumped together. It is difficult to explain how a space this large could become so completely empty in the time since the universe began. Some think smaller voids might have merged together over eons, sweeping away everything in their path to create this giant expanse of nothing. As we contemplate this cold, quiet desert, we are reminded that the universe is dominated by a deep and silent void, rather than the bright stars that dot the night sky. The cosmic web. Imagine holding a damp kitchen sponge in your hand, or observing the delicate bubbles of soapy foam resting on top of dishwater. In this structure, we find thin walls and strands of soapy water wrapping around hollow pockets of air. The soap itself takes up very little space. Almost all the volume is just trapped air, empty bubbles held in place by a fragile network. This common kitchen sight is actually one of the best ways to imagine the shape of our entire universe on the largest scale. If we could step back and observe the cosmos as a whole, we would not see a random scattering of stars. Instead, we would see a giant cosmic web. The galaxies, stars, and planets are not spread out evenly. They are gathered together along thin, glowing filaments, like bright threads woven through the darkness. These filaments cross paths and meet at bright hubs, creating a vast, glowing net. But the most striking part of this structure is not the glowing threads. It is the spaces between them. Just like the bubbles in soapy foam, the universe is filled with enormous pockets of absolute nothingness. These are the cosmic voids. They are giant, spherical regions where almost nothing exists. No stars, no planets, and very few galaxies. While the filaments contain billions of star systems, they take up only a tiny fraction of space. The vast majority of the volume in the universe is located inside these giant empty bubbles. How did the cosmos end up looking like a sponge? The story begins billions of years ago, when the universe was very young and matter was spread out almost perfectly smoothly. But there were tiny differences. Some areas had slightly more matter than others. Because gravity pulls things together, these slightly denser regions began to pull in matter from their surroundings. Over billions of years, this process grew stronger. Gravity pulled gas and dust out of the emptier regions and dragged them toward the denser areas. The empty spaces became emptier, and the crowded spaces became more crowded. The matter was stretched out into long sheets and thin strings, leaving behind clean, empty voids. The voids grew larger and larger as gravity swept the remaining matter into the walls of the cosmic web. When we gaze up at the night sky, we often focus on the bright points of light. But the true shape of the cosmos is defined by its emptiness. We live on a tiny speck of dust, clinging to a thin thread of matter, surrounded on all sides by silent, yawning bubbles of nothing. Dark energy expansion. If we contemplate the night sky, we naturally expect that gravity is the ultimate ruler of the cosmos. For a long time, scientists believed that all the matter in the universe, all the billions of stars and massive galaxies, would act like a giant cosmic brake. We assumed that the mutual gravitational pull of everything in existence would slowly drag the expansion of the cosmos to a crawl, perhaps even halting it entirely one day. But in the late 90s, astronomers studied distant exploding stars and discovered something that turned our understanding of the cosmos upside down. The expansion of our universe is not slowing down at all. Instead, it is speeding up. It is accelerating, pushing everything apart faster and faster with every passing second. Imagine tossing a ball straight up into the air. You expect it to slow down, pause at its peak, and fall back into your hands. Now imagine throwing that same ball and conceiving of it flying upward, moving faster and faster the higher it gets, accelerating into the clouds as if propelled by some invisible rocket. That is what our universe is doing right now. The engine behind this runaway cosmic expansion is what we call dark energy. It is not located in any one object or place. Instead, it seems to be a fundamental property of empty space itself. This implies that the vast voids of the cosmos are not inert. They are active players in the story of our universe. When we think of empty space, we often think of nothingness, a mere stage where matter performs its dance. But space is a physical thing, and it has a cost. Every single cubic inch of empty space contains a tiny, constant amount of dark energy. At small scales, this energy is completely unnoticeable. It does not affect daily life, and it does not affect the orbit of the Earth around the Sun because gravity at these short distances is far too strong. If you examine a room, the dark energy inside it is far too weak to push the walls apart. The gravity of the Earth and the electromagnetic forces holding the walls together easily overwhelm this gentle expansion. But when we measure the vast gulfs between galaxies, the scale changes. In these massive voids, where matter is sparse and gravity has weakened to a whisper, the subtle power of empty space begins to show itself. As the universe expands, more empty space is created in the gaps between these distant galaxies. And because dark energy is a property of space itself, as more empty space is created, the total amount of dark energy in the universe grows along with it. While gravity becomes weaker as objects move farther apart, dark energy does not dilute. It remains just as strong per unit of space as it was billions of years ago. As the gaps widen, dark energy begins to dominate. The influence of dark energy grows stronger and stronger as the universe grows larger. This energy exerts a smooth, negative pressure that pushes outward on the fabric of space-time. It is a quiet, steady push, working from within the void itself, driving galaxies away from one another. We are living in a universe where the vacuum is actively stretching, creating more of itself, and using that new space to accelerate the separation of everything. Eventually, this constant stretching will push distant galaxies so far away that their light will never be able to reach us again, leaving our local neighborhood isolated in a cold, quiet cosmic dark. It makes us realize that the emptiness we often ignore is actually the most powerful force shaping the future of our universe. But how does empty space itself move, and can it carry waves of its own? Ripples in spacetime. Imagine you are floating in a completely quiet, dark room. You cannot see anything, and you cannot hear anything. It is easy to feel as though you are surrounded by absolute nothingness. But then, you feel a faint shudder, a gentle vibration passing right through you, like the swell of a wave in the ocean. This is very close to how physicists felt in the year 2015, when they detected something that changed our understanding of the universe forever. For the first time, scientists at the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves. These waves were born 130 billion years ago, when two massive black holes collided in the deep darkness of space. The collision was so violent that it shook the universe. It sent ripples outward, traveling across the cosmos at the speed of light, until they finally washed over Earth. To detect these ripples, scientists built two giant detectors, each with long perpendicular arms stretching 4 kilometers into the landscape. Lasers measured the lengths of these arms with extreme precision. As the gravitational wave passed through our planet, it physically stretched one arm and squeezed the other. The change in length was tiny, less than 1/10,000th the width of a single proton. It was a change so small that it is almost impossible to imagine, yet our instruments registered it. This event reveals that what we call empty space is not a passive, blank backdrop. Space is a dynamic, physical medium. It can bend. It can wiggle. It can transmit energy across billions of light years. When those black holes collided, they shook space itself, like a heavy stone dropped into a calm pond. The ripples that traveled outward were waves of space, stretching and squeezing the distance between objects. When we think of empty space, we often think of a void, a lack of anything. But these cosmic ripples tell a different story. They tell us that the vacuum is flexible, responsive, and alive with activity. It is a fabric that can be warped and creased. Every time a massive object moves, accelerates, or collides, it sends tiny tremors through this fabric. We are living in a universe where the seemingly solid ground beneath our feet and the empty space we move through are constantly humming with the distant echoes of cosmic events. It reminds us that emptiness is not the absence of existence, but rather a silent canvas that holds everything together, capable of carrying the deepest whispers of the cosmos. The black hole singularity. Imagine a star, many times larger than our Sun, running out of fuel. For millions of years, its own intense gravity has been trying to pull everything inward, while the nuclear furnace at its core pushed outward. But now, that furnace goes cold. Without that outward pressure, the balance is broken. Gravity wins. The entire mass of this colossal star begins to fall inward, collapsing under its own weight. It falls faster and faster, crushing down into a smaller and smaller space. In the final moments, the collapse becomes unstoppable. The matter is squeezed past the density of common elements, past the density of atomic nuclei, until it crosses a point of no return. What remains is not a giant solid ball, but a hole in the fabric of the universe itself. All of that star, all those millions of tons of matter, is crushed into an infinitely small point. Physicists call this the singularity. It has zero volume, meaning it takes up no physical space at all. Yet, it contains the entire mass of the collapsed star. It is a point of infinite density, where our normal understanding of physics breaks down completely. But when we think of a black hole, we do not imagine this tiny point. What we perceive is the event horizon. This is the boundary of no return, a sphere of darkness that marks the region where gravity is so strong that even light cannot escape. Inside this boundary, there is only empty space. The boundary itself is not a physical surface. You could pass through it and feel nothing unusual at that exact moment. It is merely a threshold in space. Consequently, a black hole is mostly a vast, silent void. The entire structure is a giant sphere of nothingness, enclosing a single, infinitely small point of matter at the very center. It represents the ultimate expression of matter collapsing into nothingness. A massive star, once bright and full of energy, is reduced to a shadow, a pocket of pure gravitational force surrounding a tiny point of infinite density. If you were to fall into this shadow, you would travel through miles of quiet, empty space before reaching the center. The vast majority of the black hole is simply empty space, bent and warped by the gravity of the singularity. It is a striking reminder of how little substance there is in the universe and how easily matter can be squeezed away. When we contemplate the universe, we often think of objects as solid and permanent. We think of stars and planets as enduring features of the cosmos. Yet, the existence of a black hole shows us that solidity is temporary. With enough gravitational force, the empty spaces within matter are squeezed out, leaving behind a void that is defined only by its boundary. What happens to matter when it is squeezed so tight that the space inside atoms is completely eliminated? The neutron star collapse. Imagine holding a tiny teaspoon, the kind you might use to stir sugar into warm tea. Now, imagine scooping up a small amount of material from the heart of a collapsed giant star. If you tried to lift that single teaspoon, you would find it weighs about 6 billion tons. That is roughly the weight of a large mountain, or every single human being on Earth combined, packed into a space no larger than a sugar cube. It sounds like something out of science fiction, yet this is the reality of a neutron star. To understand how something can become so heavy and so small, we have to look at what happens when a massive star runs out of fuel. Throughout its life, a star is locked in a constant battle. The intense heat and energy pushing outward fight against the relentless inward pull of gravity. For millions of years, these forces remain balanced. But eventually, the fuel runs out. The outward pressure fades and gravity wins. With nothing left to resist it, gravity begins to crush the star inward. In a fraction of a second, The outer layers collapse, causing a massive explosion. But deep inside the core, a much quieter, stranger event takes place. The gravity becomes so intense, so overwhelming, that it begins to squeeze the very building blocks of matter. Normally, the tiny particles that make up our world like to keep their distance. Negatively charged electrons circle around the positive protons in the center of an atom. They stay apart, separated by a vast expanse of empty space. But under the immense weight of the collapsing star, this boundary is shattered. The pressure forces the electrons to crash directly into the protons. When they collide, they merge, transforming into neutral particles called neutrons. During this process, the wide emptiness that once existed between these particles is completely erased. The electrons and protons no longer have the room to move or exist as separate entities. They are packed together so tightly that the empty space vanishes. Without that space, the matter loses its volume but retains its mass. What is left behind is a sphere of matter so dense that it defies our everyday understanding. The entire star, which might have been many times larger than our Sun, is compressed down to a ball that could easily fit inside the boundaries of a small city, perhaps only 12 miles across. Because all the empty space has been squeezed out, the star no longer behaves like normal matter. In fact, it is helpful to think of the entire star as one single, giant atomic nucleus. The boundary between individual atoms has been completely erased. There are no longer distinct atoms of carbon, oxygen, or iron. There is only a continuous, extremely dense soup of neutrons, pressed together shoulder to shoulder. We can think of this as a cosmic library where all the books have been put into a giant trash compactor. Instead of pages separated by air and bindings, all the words are pressed into a single solid block of ink and paper. The information remains, the mass remains, but the space that allowed you to turn the pages is gone forever. If you could touch the surface of this dead star, you would be touching the densest solid material in the known universe. It is a place where gravity has successfully stripped away the emptiness that usually defines the world around us, leaving behind a pure, concentrated remnant of energy and mass. It serves as a quiet reminder of what happens when the vast spaces of our universe are forced to collapse, revealing the heavy reality hidden beneath. It reveals how the cosmos can take the grandest structures and compress them down into something small, silent, and immensely heavy. The Bekenstein Bound. Think of a wooden chest sitting in a quiet room. If you want to store books inside this chest, you naturally think about its depth, its width, and its height. You expect that a box twice as large in 3 dimensions will hold many more books. In our everyday world, storage capacity belongs to the 3-dimensional space inside. This makes intuitive sense. It feels like an absolute rule of the physical world. Yet, when physicists look closely at the fundamental limits of our universe, this intuitive rule breaks down in a strange way. They discovered that there is a strict limit to how much information can exist within any given region of space. This limit is named the Bekenstein Bound. And the surprise is where this limit is written. Instead of depending on the volume of the space inside the chest, the maximum amount of information depends only on the area of the outer surface. It is as if the space inside does not matter at all. The limit is determined entirely by the 2-dimensional boundary wrapping around it. If you try to pack too much information into that chest, if you try to squeeze too many particles and details into that volume, the chest will collapse under its own gravity, forming a black hole. When that happens, all the information about what was inside is preserved only on the surface of the black hole, on its boundary. The interior volume is no longer accessible, and only the surface area dictates how much information remains. This discovery changes how we look at the empty space around us. It suggests that the depth and volume we see might be a projection, a kind of illusion. If all the information about a room can be written on the walls of that room, does the space inside actually exist in the way we think it does? We are used to thinking of the universe as a vast three-dimensional stage where things happen. But physics tells us that the stage might be flat, and we are merely the three-dimensional holograms projected from the boundary. This boundary limit forces us to reconsider the nature of empty space. Perhaps space is not a hollow container waiting to be filled. Perhaps it is a projection created by the relations of information stored on the outer limits of the universe. In this view, the vast empty distances we perceive are not actually three-dimensional at all. They are the shadows of information written on a distant screen, a beautiful tapestry woven from the boundaries of reality. The holographic principle. In our exploration of black holes, we saw that the amount of information that can fit inside a space is limited by its surface area rather than its volume. This boundary limit suggests a profound shift in how we understand reality. If the information of a three-dimensional region is tied directly to its two-dimensional border, then perhaps the border itself is where the true physics is taking place. This brings us to a mind-bending concept that challenges everything we know about space. We often think of ourselves as solid creatures moving through a three-dimensional room. You can reach out and touch a wall, or walk from one side of a hallway to the other. Space feels wide, deep, and real. But physics suggests a stranger reality. Think of a common credit card. On its surface, there is a small, shiny sticker. When you tilt it, a three-dimensional image appears to float above the flat plastic. The image has depth and shape, yet it is printed on a flat sheet. The extra dimension you see is an illusion, projected from information stored on a flat surface. This is the holographic principle. It suggests that our entire universe, with its stars, planets, and deep voids, works in a similar way. The three dimensions of space we experience daily could be a projection of information written on a distant, flat boundary that surrounds us. If we look at string theory, this strange idea becomes mathematically precise. Physicists discovered that gravity and space in a three-dimensional region can be translated into the language of flat physics. Imagine a tin of soup. Everything happening inside the tin, all the complex movements of particles and the pull of gravity, can be mapped perfectly to the label on the outside. The label contains all the code needed to describe the interior. The interior space itself does not need to exist independently. It is simply a projection of the code on the boundary. Think of how computer games build a world. A programmer writes code on a flat drive, and the screen displays a vast forest or a city you can explore. You feel like you are walking through space, but you are really just interacting with code. The universe might be doing something similar on a cosmic scale. The boundary of the universe holds the code, and the space we occupy is the screen. This challenges the physical reality of the space we walk through. When you move your hand through the air, you feel nothing. You think you are moving through a void. But if this principle is correct, the space you are moving through is not actually there in the way you perceive it. The volume of the room, the distance between you and the wall, is a representation of data stored far away, at the very edge of the universe. Our perception of empty volume could be a projection of code. This perspective is unsettling. It implies that gravity and even space itself are not fundamental building blocks of reality. They are emergent properties, like a hologram. Just as a digital image on a screen is made of pixels, the physical world might be made of information. The depth of the cosmos, the vast emptiness between stars, could be a grand illusion. If space is a projection, then the division between objects might be artificial. We feel separate from the desk, the floor, and the stars. Yet, if all our information is written on the same boundary, we are deeply connected. The empty space between us is a consequence of the projection, rather than a physical barrier. We are walking through a three-dimensional theater, watching a play that is written in 2 dimensions. As you drift off to sleep, consider the possibility that you are not a body moving through a vast, cold void. You are a projection, a beautiful dance of information, shimmering on the boundary of space. The dark matter mystery. Imagine standing on a simple playground, merry-go-round late at night. If it spins slowly, you can hold onto the metal bars with ease. But if someone spins it with immense speed, the outward pull becomes too strong, and you are thrown off into the grass. Galaxies, those giant swirling collections of stars, behave in a very similar way. When astronomers measured how fast galaxies spin, they noticed something impossible. The stars at the outer edges are moving at speeds that should fling them away into the deep, dark void of space. The gravity from the visible stars and gas is simply not strong enough to hold them. By all the laws of physics we know, these cosmic carousels should fly apart. Yet, they stay together, spinning in perfect order. It is as if some unseen hand is holding them in place. Scientists realized there must be a massive amount of invisible matter creating the extra gravity needed to keep the galaxies intact. We call this mysterious substance dark matter. The word dark does not mean it is black like charcoal or soot. It means it is completely transparent, like water or clean air, but even more elusive. It does not reflect light, it does not absorb light, and it does not emit light. If you shone a flashlight at a clump of dark matter, the beam would pass straight through it as if nothing was there. It is a presence that remains completely hidden from our eyes and our instruments. This invisible substance does not interact with the matter we can touch and feel. A cloud of dark matter could drift right through your room, through your body, and through the core of the entire planet Earth without hitting a single atom. It is like a ghost passing through a brick wall, leaving no trace behind. The only way we know it is because of its weight. Its gravity pulls on the stars we can see, acting like a silent cosmic glue that prevents the galaxies from dissolving into the night. Without this gravitational anchor, the Milky Way would have drifted apart long ago, and our solar system might never have formed. In fact, this invisible substance is far more common than the normal matter that makes up you, the trees, the oceans, and the stars. For every gram of normal matter in the universe, there are about 5 grams of dark matter. It forms a vast, invisible scaffolding throughout the cosmos, a web of silent threads that guides the growth of galaxies. The stars and planets we see are merely tiny decorations clinging to this silent, unseen structure. We live in a universe dominated by a substance we cannot see, touch, or feel. Yet it holds our entire reality together, keeping us anchored in the void. Thermal noise in space. Think of sitting near a fireplace on a cold evening. You can feel the warmth brushing against your skin, even if you do not touch the glowing logs. That heat travels to you as invisible waves, filling the air between you and the fire. In the cold darkness of outer space, we often imagine a quiet, freezing void where nothing exists. We think of it as a perfect nothingness. But a perfect vacuum is actually an impossibility in our universe. To have a true, complete void, we would need to reach a temperature of absolute zero, a point where all motion and all energy stop completely. But nothing in the cosmos can ever reach that quiet state. Instead, the universe is filled with a gentle, invisible glow. Every star that burns sends out streams of light and heat, traveling across billions of light years. Even the ancient remnant of the beginning of time itself, the cosmic microwave background, warms the fabric of space. This relic radiation is everywhere, acting like a faint, warm blanket draped over the cosmos. If you were to float in the deepest, most remote gap between galaxies, millions of light years from the nearest star, you would still be bathed in this quiet energy. Photons, which are tiny packets of light, are constantly passing through that space. They carry heat, vibrating the vacuum. Space is never truly cold, and it is never truly empty. It is constantly humming with the thermal whispers of the cosmos, a restless sea of radiation that connects everything. The void is alive with the warmth of a universe that refuses to be completely still. Every cubic centimeter of space contains these whispers, so that emptiness is always filled with the quiet heartbeat of starlight. The wave function. Let us begin by thinking about a tiny piece of matter, like a single electron. For a long time, scientists thought of these tiny objects as tiny marbles, solid little balls of matter flying through the darkness of space. If you throw a marble at a wall with two vertical slits cut into it, the marble will go through one slit or the other. It chooses a single path. If you throw thousands of marbles, they will form two neat columns on the wall behind the slits. But when scientists set up this exact experiment with electrons, sending them toward two tiny slits one at a time, something strange happened. Even though the electrons were sent one by one, with plenty of time between them, they did not build up in two simple columns. Instead, they began to form a pattern of stripes, a striped pattern that only waves can make. It was as if each single electron traveled through both slits at the same time, interfered with itself like a ripple in a pond, and then landed on the screen. The electron, which we thought was a tiny solid particle, behaved like a wave. This experiment forces us to change how we think about empty space and the things moving through it. An electron does not travel along a single, neat path. When it is left alone, traveling through the darkness, it does not exist at one specific point. Instead, it exists as a wave of probability, spreading out across space. Physicists call this the wave function. You can think of it as a cloud of possibilities, a mathematical description of all the places the electron could possibly be. It is a map of potential positions, where some areas are highly likely and others are nearly impossible. In this state, the electron is not a solid object. It is a whisper of potential. It is everywhere, nowhere at once, rippling through the void. The empty space is not actually empty. It is filled with these overlapping waves of potential outcomes. Only when the electron hits the detector, or when we try to measure exactly where it is, does this cloud of possibilities vanish. At the moment of measurement, the wave function collapses, and the electron suddenly chooses a single, solid point to exist. This process is one of the deepest mysteries in physics. Before we look, the universe is a fluid dance of probabilities, where particles behave like waves washing through the dark. Our act of looking, of interacting with the system, forces the universe to make a choice, turning a cloud of potential into a single event in time and space. We live in a world built on these quiet, invisible waves of possibility, constantly collapsing into the reality we see around us. The solid world we touch is born from this soup of probabilities. Quantum tunneling barriers. Think about tossing a tennis ball against a brick wall. You throw it, and it bounces back into your hand. You throw it again, and the same thing happens over and over. In our everyday experience, solid objects stay on their own side of a barrier. A wall is a boundary, absolute and final. But if you were to shrink that tennis ball down to the size of a single subatomic particle, the rules of the universe change completely. If you throw a quantum particle at a barrier, most of the time it will bounce back, just like the tennis ball. However, if you keep throwing it, eventually something strange happens. The particle simply appears on the other side of the wall, moving along as if the barrier were never there. It does not punch a hole through the wall. It does not break the barrier. It simply exists on the other side, undisturbed. This happens because the subatomic world is not made of solid, localized little marbles. Instead, a particle is spread out through space as a probability wave, a gentle ripple of possibilities. This ripple represents the chance of finding the particle in any given spot. When this ripple meets a barrier, it does not stop abruptly. Because the barrier itself is mostly empty space, the ripple can leak through. The wave dampens inside the wall, but a tiny, fading portion of it manages to bleed out onto the far side. It is like a whisper passing through a heavy door. Because a small portion of the probability wave exists beyond the barrier, there is a real, measurable chance that the particle will suddenly materialize there. The barrier has not been broken, yet the particle has crossed it. It has tunneled through the solid obstacle, using the empty spaces within the structure to redefine its position. This process, known as quantum tunneling, is the reason the sun shines. Deep within the core of the sun, hydrogen atoms want to fuse together to create helium, releasing the light and warmth that sustains life on our planet. But these atoms carry positive electric charges, and they repel each other with immense force, acting like a solid wall. The temperature inside the sun is actually not hot enough to force them together. By all the laws of classical physics, the sun should be dark. But because of this gentle leaking of probability, hydrogen nuclei can tunnel through that electric barrier. They slip through the empty space of the repulsive force, coming close enough to fuse. Without this quiet quantum trick, our star would never have ignited, and our world would be cold and dark. The speed of light limit. Why is it that information cannot travel instantly from one side of the cosmos to the other? If we flick a switch here, why does a light signal take time to cross the dark void? We often think of empty space as a passive stage, a quiet background where things happen. But space has properties. It has physical constants built into its very structure, rules that govern how quickly fields can ripple and shake. These rules act like a cosmic speed limit. When we talk about the speed of light, we are talking about more than the speed of a beam of light. We are talking about the speed of causality. This is the absolute limit of how fast a cause can lead to an effect. Consider a row of dominoes stretching across the galaxy. One domino cannot fall until the one behind it knocks it over. In the same way, one part of the empty universe must physically nudge the next part to pass a signal along. That nudge takes time. The vacuum of space is a tightly woven fabric of fields. When an electron moves, it wiggles the electromagnetic field. That wiggle travels through the field at a set speed, much like a wave traveling across the surface of a quiet pond. It cannot go faster because the field itself has a built-in resistance to change. Two electrons separated by a distance do not interact instantly. They must exchange tiny ripples, packets of energy that travel through the vacuum. If you shake one electron, the other does not move until the wave reaches it. This delay is a built-in feature of the universe. It is the time it takes for empty space to transmit the news of change. If the sun disappeared this very second, we would keep orbiting a ghost sun for over 8 minutes. We would remain in the dark, warm, and secure, completely unaware of the disaster because the gravitational news has not reached us yet. The empty space between us and the sun acts as a buffer, preventing the change from being felt instantly. The speed of light is the velocity of information itself, the pace at which the universe updates its own state. It is a fundamental property of the vacuum, a sign that even empty space has a texture, a resistance, and a rhythm. It governs how we experience time and distance, ensuring that cause always precedes effect. Without this limit, the universe would happen all at once, a chaotic flash of simultaneous events. If gravity travels at this speed, What happens if we consider gravity as the shape of space itself rather than a force? The shape of spacetime. Consider a large, flexible sheet of dark rubber stretched tight between four posts. It hangs there, perfectly flat, silent, and still. Now, place a heavy bowling ball right in the center of this sheet. Under the weight of the ball, the rubber yields. It sinks downward, stretching and sloping, forming a deep bowl-shaped dip in the fabric. The flat sheet is no longer flat. It has a shape now, a slope that plunges toward the heavy ball. If you take a small glass marble and gently flick it across the rubber sheet, it does not travel in a straight line. As the marble rolls near the dip, it begins to curve. It sweeps around the bowling ball, tracing a spiral path. If the marble has enough speed, it might loop around the center several times before finally spiraling in. If it travels fast enough, it might even circle the ball indefinitely, trapped in the slope of the rubber. For centuries, people thought of gravity as an invisible pull, like a ghostly rope stretching across empty space to tug on distant objects. When an apple fell, or when the moon circled our planet, we imagined a silent force reaching out through the dark void to pull them. But there is a different way to understand this. There is no invisible rope. There is no force pulling across the void. Instead, the empty space itself is like that rubber sheet. We often think of space as nothing, a mere stage where things happen. But space is not nothing. It is a fabric, a dynamic medium that can bend, stretch, and curve. When a massive object like our Sun sits in space, it bends the fabric of space around it. The Sun does not actively pull on the Earth. The Sun simply rests in the fabric, creating a deep bend in the fabric of space. The Earth is like the marble. It is simply traveling forward, moving along the straightest possible path in a space that has been bent. As the Earth moves forward, it follows the curves and slopes created by the massive Sun. What we feel as gravity is actually the shape of space itself. A famous physicist once described this relationship by saying that matter tells space how to curve, and space tells matter how to move. It is a beautiful dance of cause and effect. The presence of mass changes the very shape of the emptiness around it. In turn, that curved emptiness guides the motion of everything that travels through it. This changes how we perceive the universe. The vast empty space between stars is not a passive vacuum. It is an active participant in every movement, every orbit, and every fall. When you drop a cup, it does not fall because the Earth is grabbing it. It falls because the Earth has bent the space around it, and the cup is sliding down the slope of that bent space. Even light, which has no mass at all, must follow these curves. As a beam of starlight travels through the deep dark of the universe, it bends when it passes near a massive galaxy. The light is not pulled by gravity in the traditional sense. It is simply traveling along the natural contours of a warped space. So, when we look up at the night sky, we can think of space not as a silent emptiness, but as a vast, invisible landscape of valleys and slopes, shaped by the stars and planets that rest within it. We are all moving through these unseen curves, guided by the very shape of space itself. The Big Freeze. Let us sit with the image of a story ending with a quiet, fading sigh instead of a sudden flash of light. This is the final chapter of our universe, a time that scientists call the Big Freeze. If we could watch this happen over trillions of years, we would see the great cosmic dance slowly wind down. The space between everything keeps growing, stretching out until the distances become too vast to comprehend. We are used to thinking of the universe as a busy place, filled with colliding galaxies and burning stars. But this activity is just a brief moment in the life of the cosmos. Imagine standing on a planet in the far future. When you look up at the night sky, you see nothing. The other galaxies, which once painted the darkness with billions of stars, have drifted so far away that their light can no longer reach us. They have slipped beyond the horizon of the observable world, leaving each galaxy to face the dark alone. Our cosmic neighborhood becomes an isolated island in an endless silent ocean. There are no neighbors to see and no way to cross the void. Within our own galaxy, the lights are going out. Stars are the engines of the cosmos, burning through their fuel to keep the cold at bay. But that fuel is finite. One by one, the stars burn through their hydrogen, swelling and then shrinking into cold, dead embers. The brilliant blue giants go first, followed by stars like our Sun, and finally, the small red dwarfs that burned slowly for trillions of years. What remains are cold spheres of iron and carbon, floating silently in the dark. These cold iron remnants are the tombstones of a once vibrant cosmos. Time continues to march forward on a scale that makes the entire history of human existence seem like a single heartbeat. Eventually, even these solid iron remnants begin to fade. The very particles that make up matter, the protons and neutrons that once formed planets and trees and oceans, begin to decay. Over unimaginable spans of time, the solid matter dissolves, melting away into the expanding void. What is left is a universe of absolute stillness. There are no stars, no planets, and no warmth. Only a few stray particles of light, stretched out so long that they carry almost zero energy, drift through an infinite expanse of empty space. The temperature drops to almost absolute zero. In this final state, the universe has achieved its ultimate form, a perfect, unchanging emptiness where nothing ever happens, and nothing ever will. It is a quiet end, a return to the silence from which everything first emerged. Black hole radiation. Imagine a place in the universe where gravity is so intense that nothing, not even light, can escape. We call these regions black holes, and for a long time, we believed they were eternal tombstones, destined to last forever. But in the middle of the 1970s, the physicist Stephen Hawking suggested a different story. He proposed that black holes are not completely permanent. Instead, they are slowly leaking, evaporating away into the cold quiet of space. To understand how a giant cosmic trap can leak, we have to consider the very edge of the black hole, a boundary called the event horizon. This is the point of no return. Right at this border, the empty fabric of space is constantly bubbling with activity. Pairs of tiny virtual particles constantly pop into existence out of the empty air, cling to each other for a brief fraction of a second, and then vanish back into nothingness. Usually this dance happens so fast that we can never detect it. But when this dance happens right on the edge of the event horizon, the rules change. Imagine two partners dancing on the very brink of a canyon. Suddenly, one partner slips over the edge, falling into the dark depths. The other partner is left standing on the ledge with no one to pull them back. Near a black hole, one particle falls past the point of no return, trapped forever inside. The remaining partner is left stranded on the outside. Without its companion to recombine with, this lonely particle escapes into the wide universe. When this happens, the escaping particle does not leave for free. It needs energy to become a real, permanent particle. It takes this energy directly from the gravitational pull of the black hole. Because energy and mass are two sides of the same coin, the black hole loses a tiny fraction of its weight every time a particle escapes. This slow shedding of mass is happening across the cosmos right now. Every black hole is slowly bleeding away its essence. The darkest, most terrifying objects in the cosmos are temporary guests rather than permanent fixtures. This process is agonizingly slow. For a typical black hole, it takes a number of years so large that we do not even have a common name for it, a number with more than 60 zeros. But as the black hole gets smaller, the evaporation speeds up. In its final moments, the black hole shrinks faster and faster, releasing its remaining energy in a quiet flash. Eventually, the black hole dissolves completely, leaving behind nothing but empty space. The universe cleanses itself of these dark giants, returning their stolen mass back to the quiet void. The Planck length limit. Imagine we want to zoom into the very fabric of the room around you. We might start with a grain of sand, then go down to a single cell, then down to an atom, then a proton. We usually think of space as a smooth, endless background, a perfect stage where these tiny players act out their lives. We assume that no matter how small we go, we can always go smaller, dividing distance in half, and then in half again, forever. But nature has a hard boundary, a final flaw where the very concept of physical distance begins to shatter. This boundary is known to science as the Planck length, a scale so unimaginably tiny that it is written as 10 to the minus 35 meters. To put this size in perspective, if a single atom were blown up to the size of the entire observable universe, the Planck length would only be about the size of a regular tree. It is a scale that defies our everyday experience and challenges our understanding of reality. At this level, the smooth, comfortable geometry of our world ceases to exist. Consider a smooth sheet of paper. From a distance, it feels perfectly flat and continuous. If you glide your finger across it, it feels like one seamless object. But if we examine that paper under a powerful microscope, we discover the rough fibers, the gaps, and the uneven texture. Go down even further, to the level of atoms, and the paper is no longer a solid surface. It is a collection of isolated particles separated by vast voids. Space itself behaves in a similar way. We experience space as a smooth, continuous fabric. We glide through it without feeling any bumps, cracks, or seams. But if we could zoom in past the Planck length, we would find that space is pixelated. It is made of indivisible units, like the tiny pixels on a digital screen. You cannot stand between two pixels. You are either on one or you are on the next. There is no in-between. There is no half pixel of space. Below this scale, the concept of a path or a straight line loses all meaning. The smooth fabric of space breaks down entirely. It becomes a wild, churning environment known as quantum foam. Here, the rules of gravity and quantum mechanics clash in a chaotic dance. Tiny black holes might form and vanish in a fraction of a second. Wormholes could open and close, linking random points in space and time. In this realm, the distinction between space and time dissolves. You can no longer say that one event happened before another, or that one point is next to another. The coordinates we use to map our world break down, leaving only a turbulent sea of pure energy fluctuations. If we try to measure something smaller than this limit, we run into a fundamental wall. To detect something so tiny, one would need to use light with an extremely short wavelength. A short wavelength requires an immense amount of energy. If we tried to pack enough energy into a region smaller than the Planck length to measure it, we would concentrate so much mass and energy into that tiny spot that we would create a miniature black hole. That black hole would instantly swallow the very region we were trying to measure, hiding it from the universe forever. Nature guards its smallest secrets behind a shield of gravity. We are left with a picture of a universe that is grainy instead of smooth. We live our lives on a grand scale, floating on top of a turbulent, chaotic ocean of quantum foam. What we perceive as empty space is actually a vast network of tiny, shifting pixels, vibrating at the absolute limit of existence. The fine structure constant. Have you ever considered that the entire fabric of our reality, the very space inside every atom, is held in a delicate balance by a single, quiet number? Scientists have discovered a specific value that appears everywhere in the equations of the cosmos. It is a pure number, with no units of scale or measurement attached to it. It is approximately 1/137. This number is known as the fine structure constant. It dictates the strength of the connection between light and matter. More specifically, it determines how tightly an electron is bound to the nucleus of an atom. You can think of it as a cosmic volume knob that sets the strength of the electromagnetic force. If you turn this knob even slightly, the entire structure of the universe changes. If this number was slightly larger, the attraction between electrons and the nucleus would be much stronger. Electrons would be pulled inward, shrinking the size of atoms. The vast, empty space that defines the interior of an atom would contract. Matter would become denser, and the chemistry that allows complex molecules to form would break down. Stars would burn through their fuel at a different pace, and the elements needed for life might never form in the heart of giant stars. On the other hand, if this number was slightly smaller, the bond would weaken. Electrons would drift further away from the nucleus, expanding the atom. In a universe like that, atoms would be bloated and fragile. They would easily fall apart, unable to hold their shapes. The delicate dance of chemical bonds would dissolve, and solid objects could not exist. The balance between empty space and solid matter would be ruined. Our universe rests on the knife edge of this single value. It is this precise ratio of 1/137 that keeps atoms at the exact size they are. It ensures that electrons maintain their stable orbits, leaving the vast interior of the atom empty, yet stable. This number defines the scale of everything we touch and see, from the grand sweep of a galaxy to the quiet stillness of a sleeping mind. It dictates how light scatters, how crystals grow, and how molecules interact. Physicists have spent decades trying to understand why this specific value exists, but its origin remains a deep mystery. It is a quiet guide that operates in the background of every physical interaction. Without this exact strength, the emptiness of the cosmos would either collapse into dense packets of energy or dissolve into a structureless fog. We exist because this number is exactly what it is, maintaining the vast, silent spaces that make up our world. The ghostly neutrino. Imagine your thumb for a moment. Right now, in the span of a single second, about 100 trillion tiny particles called neutrinos are streaming right through your thumbnail. They do not leave a mark. They do not slow down. They do not touch a single part of you. They are created in the hearts of distant stars, in giant cosmic explosions, and in the nuclear furnace of our own sun. They flood the cosmos, traveling almost at the speed of light, passing through planets, stars, and people as if we were nothing more than ghosts. How do they do this? If you try to push your hand through a brick wall, you are stopped immediately. Your hand feels solid, and the wall feels solid. Yet, to a neutrino, that brick wall is as wide open and transparent as a clear summer sky. In fact, a neutrino could travel through a block of solid lead that is 6 trillion miles thick, and it would likely pass right through to the other side without bumping into a single thing. This happens because neutrinos are almost completely weightless, and they carry no electric charge. Because they have no charge, they are completely immune to the electromagnetic forces that keep atoms apart. When we touch a table, we are not actually touching solid matter. We are feeling the electric fields of our atoms pushing back against the electric fields of the table. A neutrino does not feel this push. It sails right through the electronic barriers that make our world feel solid. To a neutrino, the universe is revealed for what it actually is: an immense, silent void. The solid ground beneath our feet, the heavy mountains, the deep oceans, and even our own bodies are mostly made of empty space. The atoms that make up our world are like lonely solar systems, with vast stretches of nothingness between the tiny nuclei and the distant clouds of electrons. A neutrino is so small and so completely indifferent to electromagnetic forces that it easily slips through these enormous gaps. We live in a world defined by the illusion of solidity. We build houses to keep out the wind, and we wear clothes to keep out the cold. But to these ghostly particles, our solid Earth is just a faint mist, a gentle shadow that easily lets them pass. They remind us that the physical world we touch and experience is only one way of experiencing reality. Beneath the surface of our everyday lives lies a universe that is almost entirely empty, a vast and silent space where the ghostly messengers of the cosmos travel forever without ever touching the ground. The Dirac Sea. In the late 1920s, a physicist named Paul Dirac was looking at his equations and noticed something strange. His mathematical descriptions of the electron suggested that particles could exist with less than zero energy. This seemed impossible at first. How could something have negative energy? To solve this puzzle, he came up with a beautiful, mind-bending picture of the universe. He imagined that what we call empty space, the quiet vacuum, is actually not empty at all. Instead, he proposed that the vacuum is an infinite, silent sea filled to the brim with electrons occupying these negative energy states. We cannot see or feel this sea because it is completely full and perfectly uniform, like a calm, featureless ocean. It is the baseline of reality, a peaceful and unseen backdrop to our world. But then, Dirac suggested, what if we add a splash of energy to this sea? If we strike one of these hidden electrons with enough energy, we can kick it out of the sea into the visible world, where it becomes a normal, positive energy electron we can measure. But when that electron leaves, it leaves behind a hole in the negative energy sea. This hole behaves like a bubble rising through water. Because it is the absence of a negative electron, the hole itself appears to have a positive charge. It acts like a real particle, identical to an electron, but with the opposite electric charge. Today, we call this hole a positron, the first piece of antimatter ever predicted. Dirac had discovered antimatter simply by imagining the vacuum as a crowded, invisible ocean. His theory suggested that the void is not empty space, but rather a deeply filled space, waiting to be disturbed. Quantum entanglement connection. Suppose we have two custom dice. You roll one in New York, and it lands on a 6. At that exact same millisecond, your friend rolls the other die in Tokyo, and it lands on a 1. You repeat this thousands of times. Every single time you roll a 6, your friend rolls a 1. Every time you roll a 2, your friend rolls a 5. The two dice always add up to 7, no matter how quickly you roll them, and no matter how far apart you are. There is no physical connection between them, no hidden wires, no signals passing back and forth. They simply dance in perfect harmony across the globe. Albert Einstein looked at this concept in the quantum world and found it deeply unsettling. He called it spooky action at a distance. He resisted the idea because it seemed to break the cosmic speed limit of the universe, which is the speed of light. In our everyday world, if you want to send a message to someone far away, that message has to travel through the space between you. It takes time. Even light, the fastest thing we know, needs time to cross a room, a continent, or the wide void between stars. Yet, in the quiet depths of quantum physics, particles can become entangled. When two subatomic particles interact in a specific way, they form a shared identity. They cease to be two separate objects and become a single system described by a single mathematical wave. If you separate them by the width of a room or the width of a galaxy, this shared identity remains intact. When you measure the state of one particle, say its direction of spin, you instantly know the state of its partner. If one spins clockwise, the other immediately spins counterclockwise. This does not happen because a signal traveled from the first particle to the second. We know this because the response is instantaneous. If a signal were traveling through space, it would have to travel faster than light, which is impossible under our current understanding of modern physics. Instead, the connection seems to bypass space entirely. It is as if the physical distance between the two particles does not exist for them at all. The vast empty space separating them is, in some strange way, an illusion. This behavior challenges our deepest assumptions about reality. We tend to think of space as a giant container, a physical stage where objects sit and move. In this view, if two things are far apart, they are separate. They cannot influence each other without something crossing the gap between them. But quantum entanglement suggests a different picture. It implies that, at a fundamental level, the universe is connected in ways that do not care about distance. Perhaps space is not a fundamental building block of reality, but rather a secondary property that emerges from a deeper, interconnected web. The empty void between stars might not be a barrier at all. It may just be a surface-level projection, like the space between 2 points on a single piece of folded paper. When you fold the paper, the 2 points touch, even though they look far apart when the paper is flat. This leaves us with a quiet, unsettling thought. If space does not truly separate the fundamental pieces of our universe, then the vast, lonely distances in the night sky might be far less empty than they appear. The empty void may not be a divider, but a canvas where everything remains secretly and instantly in touch. The Mach Principle. Let us begin with a simple experiment in the mind. Imagine you are floating in a dark, completely empty universe. There are no stars, no planets, no other people, and no light. It is just you, suspended in a limitless void. Now, imagine you begin to spin around and around. In our everyday world, if you spin fast, your arms are pulled outward away from your body. You feel the tug of what we call centrifugal force. But in this empty void, would your arms still fly out? Would you feel any force at all? This question is at the heart of an idea proposed by the physicist Ernst Mach. He argued that if the universe were completely empty, you could not even define what it means to spin. If there are no distant stars or galaxies to measure yourself against, how do you know you are rotating at all? Without other matter in the cosmos to provide a frame of reference, there is no difference between standing still and spinning. Mach suggested that the physical sensation of rotation, the very force pulling your arms outward, only exists because the rest of the universe is there. The distant stars are pulling on you, defining the boundary between movement and stillness. When you feel the tug of inertia, whether it is the pull on your arms as you spin, or the slide of your body to the side when a car turns a corner, you are feeling a connection to all the matter in existence. The distant galaxies, the stars billions of light years away, and the dust floating in deep space are all participating in your local experience of movement. The weight of your own body and its resistance to change are not properties you possess in isolation. Instead, they are created by your relationship to everything else. If the universe were empty of everything except you, your mass and your weight would lose their meaning. Under this view, space is not an empty stage where matter performs. Space itself requires matter to have any measurable properties. Without the distant stars to anchor us, the physical rules we take for granted, like inertia and acceleration, might simply vanish. It is a thought that binds our smallest local movements to the grandest scales of the cosmos. Every time you turn around or feel the weight of your own step, or catch yourself as you stumble, you are experiencing a quiet dialogue between your body and the entire universe. You are feeling the collective influence of every distant star. 0-point energy. Let us think about what happens when we cool something down. In our everyday experience, warmth is simply the motion of atoms. When things are hot, those tiny particles dance and shake with energy. As we cool them down, their movement slows. If we push this process to the absolute limit, down to the coldest possible temperature in the universe, a point we call absolute zero, we might expect everything to come to a complete standstill. It is natural to imagine a state of perfect quiet, where all movement ceases and the universe finally becomes completely still. But the rules of the quantum world tell us a very different story. According to these laws, a particle can never be completely at rest. If a particle were to stop moving entirely, we would know its exact position and its exact speed at the same time. The fundamental laws of physics do not allow us to know both things with perfect certainty. Because of this uncertainty, even at the absolute coldest temperature imaginable, a small, irreducible amount of movement must always remain. This residual motion is what we call 0-point energy. It is a minimum amount of energy that cannot be removed from any system, no matter how hard we try to freeze it. Imagine a swing in a park. In our normal world, we can stop the swing and keep it perfectly still at the lowest point. But a quantum swing can never sit completely still. It always retains a tiny, restless tremor, a subtle shaking that cannot be calmed. This energy is not something passing through space, nor is it left over from some outside source. It is locked directly into the fabric of space itself. It is a fundamental flaw below which the energy of the universe can never drop. So, if we were to take a region of space, empty it of all matter, shield it from every source of radiation, and cool it down to the absolute limit of freezing, it would still contain this residual hum. The emptiness is never truly inactive. It keeps a quiet, permanent restlessness that is built into the rules of nature. Emptiness is still alive with this baseline activity. If this energy is built into empty space, could it be the same energy accelerating the expansion of the entire cosmos? The cosmological constant. Albert Einstein sat at his desk, staring at the equations that described the very fabric of gravity, space, and time. He noticed something troubling. His equations showed that the universe had to be either expanding or contracting. It could not simply stand still. In those days, everyone believed the universe was eternal and unchanging. To fix this, Einstein added a small term to his math, a mathematical fudge factor he called the cosmological constant. This constant acted like a gentle, unseen pressure, balancing gravity and keeping his universe static. Later, when astronomers discovered the universe was indeed expanding, Einstein called this constant his greatest blunder. Yet, decades later, we have discovered that he was actually onto something profound. We now understand that this constant is far from a mistake. Instead, it is a representation of the energy inherent to empty space itself. If we think of a container that is completely empty, cleared of all matter, light, and radiation, it seems like nothing remains. But in the language of modern physics, that empty space still possesses a fundamental, quiet energy. It is a property of space itself, an energy density that does not dilute as the universe grows. Unlike matter, which spreads out and becomes less dense as space expands, this energy remains constant throughout every cubic centimeter of the cosmos. This brings us to a strange paradox. The value of this cosmological constant is extremely tiny. In any small patch of space, say the size of a teacup, the energy is almost imperceptible. It is the smallest energy density we have ever measured in physics. However, because the universe is so vast, And because there is so much empty space between the stars and galaxies, this tiny value adds up. When we multiply this minuscule number by the sheer volume of the cosmos, it becomes the dominant force in existence. The emptiness of space, by virtue of its massive scale, wins the cosmic tug of war. This constant serves as a bridge between the subatomic world of quantum mechanics and the grand scale of the cosmos. In the quantum realm, empty space is a boiling soup of virtual particles, which should produce a massive amount of energy. Yet, the cosmological constant we observe is tiny. This massive mismatch is one of the deepest mysteries in modern science. The quiet hum of empty space determines how the cosmos will evolve, linking the smallest building blocks of reality to the ultimate fate of everything we know. We once believed that the fate of the cosmos would be decided by the pull of its stars and galaxies. Now we understand that the real master of our universe is the quiet energy hidden within the empty space between them. It is a slow, steady push that will guide the cosmos into its distant future. De Sitter space. Imagine a universe stripped of everything we know. No stars shining in the dark, no planets drifting through the cold, no clouds of cosmic dust, only empty space stretching out in every direction. This is the mathematical sandbox physicists call de Sitter space. It is a simplified model of the cosmos containing absolutely no matter, designed to help us understand how gravity works in its purest form. In this clean, quiet world, only one thing exists: a subtle outward pressure. This pressure is dark energy. Without any matter to slow it down, this empty space does not sit still. It expands, and it does so at an accelerating rate, doubling its size over and over, forever. It is a perpetual motion machine of emptiness, growing larger and thinner with every passing moment, pulling the fabric of reality apart. Physicists use this model to study gravity without the messy complications of stars and galaxies. It acts like a clean laboratory. By removing all the clutter, we can see the pure mechanics of how space and time behave when pushed by cosmic acceleration. It helps us understand the fundamental structure of our own cosmos, offering a clear view of how gravity interacts with the energy of the vacuum. This model is more than a mathematical trick. It serves as a portrait of where our own universe is headed. As the galaxies drift further apart and the stars eventually burn out, the vast distances between things will grow so immense that the influence of matter fades to zero. The universe we inhabit will slowly transform, resembling this empty model more and more. We are living in a temporary oasis of structure, slowly drifting toward a state of pure, expanding nothingness. The dark night sky. On a clear night, the sky above appears as a canvas of deep, velvet blackness, dotted with distant points of light. It feels natural, almost obvious, that the night sky should be dark. But for centuries, thinkers puzzled over a simple question that turns this common experience into a profound mystery. If the universe is infinitely large, and if it is filled with an infinite number of stars scattered in every direction, then why is the night sky dark? Think of standing in a dense forest of ancient trees. If the forest goes on forever, no matter which direction you turn, your line of sight will eventually hit a tree trunk. You would not see any gaps, only a solid wall of wood. If the universe worked the same way, with stars instead of trees, then every single point in the sky should align with a star. The dome of the night should glow as brightly as the surface of the sun. The sky should be a solid sheet of blinding light, day and night. We would live in a cosmic oven, cooked by the light of infinite suns. This puzzle is known as Olber's paradox, and the solution reveals a deep truth about the nature of our cosmic home. The dark sky is telling us that the universe is not static and eternal. Instead, it has a beginning, and it is actively stretching. First, the universe is about 14 billion years old. Because light takes time to travel through space, we can only see stars whose light has had enough time to reach our eyes since the beginning of time. There are countless stars out there whose light is still traveling toward us, crossing the vast gulfs of space, but has not arrived yet. They are hidden behind the horizon of time. If we wait billions of years, more light will reach us. But for now, those distant corners remain dark. Second, the universe is expanding. As space stretches, the light traveling through it also stretches. The waves of light from the most distant galaxies are pulled out, becoming longer and longer. By the time this light reaches us, it has shifted from visible colors into infrared radiation and even further into microwaves. Our human eyes cannot see this stretched light. It is there, bathing the night, but it is invisible to us. The darkness of the night sky is far more than a simple absence of light. It is a cosmic shadow, a direct visual proof of the giant void. It tells us that we live in a young, expanding universe, where the emptiness is vast enough to swallow the light of 1 trillion suns. The Jeans Instability. Imagine a giant cloud of hydrogen gas drifting in the silent dark of the early universe. This cloud is caught in a quiet tug-of-war between two opposing forces. On one side, we have thermal pressure, which is simply the heat of the gas. Heat makes the individual gas particles bounce around and push outward, wanting to spread the cloud thin and keep it empty. On the other side, we have gravity. Gravity is the silent pull that wants to bring every single particle closer together, trying to squeeze the cloud into a tight ball. For a very long time, these two forces are perfectly balanced. The cloud just drifts. But what happens if the temperature drops? If the cloud becomes cold enough, the gas particles slow down and lose their energy. And if the cloud is massive enough, the balance of power shifts. Gravity starts to win the tug-of-war. This critical tipping point is known as the Jeans Instability. Once this threshold is crossed, the cloud cannot support itself anymore. It begins to collapse inward under its own weight. As the gas squeezes tighter, the particles crowd together and the temperature at the center begins to rise. Eventually, the core becomes so hot and dense that nuclear fusion ignites. The very first star lights up in the darkness. This process is the bridge between uniform emptiness and structured matter. Without this instability, the universe would have remained a cold, featureless mist of hydrogen. This simple cosmic balance is what allowed the first stars to light up the empty space, carving out islands of warmth and light in the infinite void. Cosmic microwave background. If you ever turned on an old television set to an empty channel, you probably remember the screen filling with a chaotic blizzard of black and white static, accompanied by a soft, rushing hiss. That familiar sound is partly the sound of empty air, of random electronic noise within the machine itself. But a small part of that static, about 1% of it, is something far older and more profound. It is the literal echo of the beginning of time. It is a whisper from the very first light that was ever free to travel across the cosmos. A relic of the hot and dense early universe that still floats through our rooms today. Nearly 14 billion years ago, the universe was not the vast, cold emptiness we know today. Instead, it was a thick, glowing fog of hot plasma, so dense that light could not travel far before bumping into a particle of matter. The cosmos was completely opaque, trapped in a perpetual blinding glare where information could not travel. But then, as the universe expanded, it began to cool. Eventually, electrons and protons joined together to form the very first stable atoms of hydrogen and helium. The fog cleared. In a single, silent moment, the universe became transparent. The light, which had been trapped for hundreds of thousands of years, was suddenly set free to travel in every direction through the newly opened space. Since that ancient moment, that first light has been traveling through the expanding void of space. As the universe grew larger, the very fabric of space through which the light was traveling stretched out. This stretching of space also stretched the light waves themselves, pulling them longer and longer. What began as an intense, blinding white glow was slowly drawn out over billions of years, shifting from visible light down into the infrared, and eventually into the invisible range of microwaves. Today, this relic radiation fills every single corner of the universe. It is everywhere around us, passing silently through our bodies, drifting through the dark gaps between the stars, and washing over our planet day and night. It has spent almost 14 billion years crossing the expanding void, carrying a pristine image of the infant cosmos. When we tune our instruments to detect these microwaves, we are observing a portrait of our universe captured at the exact moment it first became open and clear. It is a gentle reminder that the vast emptiness of space is never truly empty, but is instead bathed in the quiet, persistent warmth of its own creation, an ancient light that has traveled across time to reach us. The proton decay. We think of the proton as the ultimate survivor. It is the building block of every atom in your body, the oxygen you breathe, the carbon in your bones, the water in the oceans. For all of human history, and indeed the history of the Earth, we have assumed that these tiny particles are eternal. They seem to last forever, holding the material world together with absolute stability. But modern physics suggests that even the proton may have an expiration date. If you gather enough protons together, say in a giant underground tank filled with thousands of tons of ultra-pure water surrounded by thousands of light detectors, you might expect to see one of them occasionally fall apart. Scientists have built these massive detectors deep underground, shielded from cosmic rays, waiting in the silence. They watch and they wait, year after year. Yet, we have never seen a single proton decay, not even once. Despite this silence, our most advanced theories of the universe, the grand unified theories that try to unite all the fundamental forces, suggest that protons are not actually permanent. They are just immensely long-lived. The estimated minimum lifespan of a proton is 10 to the 34 years. That is a number so vast that it is difficult for our minds to grasp. It is a 1 followed by 34 zeros. To put that in perspective, the universe has only existed for about 13.8 billion years, which is a mere 10 to the 10 years. If these theories are correct, it means that even the most solid matter we see around us is slowly, imperceptibly, ticking away like a clock. On these immense timescales, the atoms that make up the stars, the planets, and our own bodies will eventually destabilize. The protons inside them will break apart, decaying into lighter particles like positrons and pions, which then annihilate into pure light. Every piece of solid matter in the cosmos is on a slow journey toward dissolution. The mountains, the cold remnants of dead stars, the dust drifting in the deep voids, all of it will eventually dissolve. The universe will be empty because things have drifted apart, and because the very ingredients of matter themselves have ceased to exist. All atomic structures will turn to light, leaving only the quiet, expanding void. But what if the empty space itself is not in its lowest energy state and could suddenly collapse? False vacuum decay. Think of a heavy wooden ball resting on the side of a steep hill. It sits in a shallow dip, a small groove on the slope. For now, it is perfectly still, appearing safe and settled. However, this stability is temporary. The ball is not at the very bottom of the hill. A deeper valley lies much further down. All it takes is a tiny nudge to send it rolling to the true bottom. In physics, our universe might be like that ball. We exist in a state known as a false vacuum. The fields that shape our reality, specifically the potential energy associated with the Higgs field, might not be at their lowest possible level. Instead, they are trapped in a temporary valley of energy, a state called metastability. We are stable enough to exist for billions of years, but we are not in the absolute lowest energy state. The true vacuum, the ultimate bottom of the hill, is still waiting. Because the subatomic world is governed by quantum mechanics, things do not always need a physical push to move. Particles can slip through solid barriers like ghosts, a process called quantum tunneling. At any moment, in any random corner of the cosmos, a tiny fluctuation could allow a small patch of space to tunnel through the energy barrier. This patch would transition from our false vacuum into the true vacuum. This creates a tiny bubble of new space. Inside this bubble, the laws of physics are entirely different. The fundamental constants that govern how particles interact, how gravity behaves, and how matter holds together would be completely rewritten. This bubble of true vacuum would be a pocket of a different kind of reality, one with a lower energy level. Once this bubble forms, it will not stay small. The true vacuum is more stable than the space around it, so it wants to expand. The outer edge of the bubble would begin to push outward, driven by the release of energy as the surrounding false vacuum collapses. This boundary would accelerate, rushing outward through the universe at the speed of light. Because it travels at the speed limit of the cosmos, there would be no warning. We would not see it coming. Light itself cannot outrun the edge of the bubble. One moment, a star is shining bright, and the next, it is gone. If the bubble formed near our solar system, it would sweep across our planet in a fraction of a second. As the boundary passes through, it would perform the ultimate reset. The atoms that make up our bodies, our air, and our planet rely on the precise balance of forces we have always known. Inside the bubble, those forces no longer exist. The chemistry that allows molecules to bind would fail. Protons and neutrons might dissolve. Every structure, from the smallest strand of genetic code to the largest galaxy, would be instantly dismantled into its most basic components. It would be a complete and final erasure. There would be no heat, no fire, no pain, just an immediate transition into a different state of being. The universe would not be destroyed in the sense of becoming nothing. Instead, it would be reborn as a new kind of space, a blank canvas where entirely different physical laws could begin to play out over billions of years. We are living in a temporary home, suspended above a deeper valley, waiting for the ground to shift beneath our feet. The human scale. Hold your hands in front of you. Feel their warmth, their weight, and their presence. If you press your palms together, they stop, unable to pass through one another. Yet we know that if we magnified your skin 1 billion times, we would find nothing but vast expanses of empty space, dotted with tiny, distant points of energy. Your hands are almost entirely emptiness. Why then does the mind insist on such a firm, solid reality? The answer lies in our history on this planet. We did not evolve to perceive the true nature of quantum voids or the slow stretching of cosmic space. Our ancestors did not need to sense the empty space inside an atom to survive. Instead, they needed to find fruit on a branch, run from predators hidden in the grass, and avoid falling off cliffs. The brain developed as a tool for staying alive, not as a window to absolute truth. To navigate a dangerous world, our senses had to simplify the universe. If we perceived the world as it truly is, a haze of electric fields and massive pockets of nothingness, we could not function. We would be overwhelmed by the sheer scale of the void. So, our brains act as a filter, translating a chaotic dance of energy into stable, solid objects. We perceive a table as solid because that perception keeps us from dropping our cup. We perceive the ground as firm because it tells us where we can safely step. Every sensation we experience is a useful shorthand. The hard edge of a table, the weight of a stone, the resistance of a wall. All of these are signals constructed by our neurology to keep us safe and grounded. We exist in a middle kingdom, a comfortable pocket of scale between the subatomic and the cosmic. We are too large to witness the quantum jitter and too small to feel the bending of spacetime across light years. What we call reality is actually a practical interface, a user-friendly map created by our biology to help us make decisions. We do not need to feel the expansion of the universe while walking down a forest path, nor do we need to calculate the probability waves of the dirt under our feet. Our biology keeps us focused on the scale where life actually happens. When you touch a stone, you are not touching solid matter. You are feeling the repulsion of fields pushing against other fields. Your mind interprets this resistance as a hard surface. It is a beautiful compromise. The universe allows us to live in a world of texture, color, and form, shielding us from the cold reality of the void. We are creatures made of emptiness who have built a home of solid dreams. The ultimate void. If we think about the dark night, a simple question often comes to mind. Why does anything exist at all, rather than absolute nothingness, in a cosmos so completely ruled by the void? It is one of those thoughts that keeps us awake, lying awake as the clock ticks away. We live in a world filled with trees, oceans, houses, and stars, so we naturally assume that existence is the main event. We think of matter as the default, and empty space as just the background. But when we contemplate the actual layout of the cosmos, we find that we have the story completely backward. Let us try a thought experiment. Imagine collecting every single speck of matter in the entire observable universe. Every grain of sand on every beach, every drop of water, every planet, every star, and every distant galaxy. If you gathered all of these physical things and squeezed them together, removing all the empty space inside the atoms, how much room would they take up? The answer is almost impossible to comprehend. All the matter in the vastness of creation would fit into a volume no larger than a single grain of sand, or perhaps a small marble. The rest of the universe, spanning billions of light years in every direction, is completely empty. This realization changes how we view ourselves and our place in existence. We are not the main characters in a crowded universe. Instead, we are rare anomalies, tiny ripples of dust in a vast ocean of quiet emptiness. The cosmos does not seem to prefer things. It seems to prefer the quiet, cold, and still void. The default state of reality is not solid matter, but space itself. We are the exceptions to the rule. When we observe the night sky, we often focus on the stars as the main features, but they are really just tiny specks of dust floating in a dark ocean that goes on forever. If you think about a blank canvas, the canvas is always there, waiting. A painter might splash a few drops of color onto it, but the canvas remains the foundation. In our universe, space is that canvas. The stars, the planets, and our own bodies are just tiny, temporary drops of paint. They are rare disturbances in a quiet, dark field that stretches out forever. If those drops of paint were wiped away, the canvas would remain untouched, perfect and still. This means that the emptiness is not the absence of reality. It is the reality. It is the very fabric that allows anything else to exist. When we walk through our daily lives, feeling the solid ground beneath our feet and breathing the air, we are participating in a very unusual event. We are living in a tiny pocket of activity, a brief moment of noise in an otherwise silent hall. Every breath we take, every word we speak, is a quiet defiance of the vast emptiness that surrounds our tiny planet. So when we contemplate the night sky, we are facing the true nature of the cosmos. The stars are beautiful, but they are just small sparks in the dark. The dark itself is the default. It is the quiet home from which everything came, and the quiet home to which everything will eventually return. Knowing this does not have to make us feel small or lonely. Instead, it can make our existence feel unusually rare and precious. We are the quiet universe, waking up for a brief moment, wondering why we are here, before returning to the peaceful sleep of the ultimate void. Identity and empty space. Imagine an ancient wooden ship docked in a quiet harbor. Over many decades, the wooden planks begin to rot. One by one, the caretakers replace each piece of wood. They swap the deck, the mast, and the hull, until every single original board is gone. Is this still the same ship that first sailed into the harbor? If we took all the old discarded planks and built a second ship with them, which one would be the true ship? This old riddle points to a quiet realization about our own bodies. We feel like we are the same person we were 10 years ago, but the physical substance of who we were has almost entirely departed. Every day, you breathe in new air and eat food, taking in new atoms. At the same time, you shed old skin cells and exhale carbon. Over the course of about 7 years, almost every single atom that makes up your body is replaced by a new one. The carbon in your muscles might have been part of a leaf last year. The calcium in your bones might have flowed through a river long ago. To make this even more strange, the matter we are made of is not even solid. If you could strip away all the empty space inside the atoms of your body, you would fit into a speck of dust so small that it could not be seen without a microscope. Yet that tiny speck would still weigh the same as you do right now. The rest of you, the vast majority of your physical form, is nothing but empty space. It is a vacuum held together by the silent tension of forces. The atoms that form this space are not permanent tenants. They are travelers passing through. Every breath you take, every glass of water you drink, and every meal you share is a quiet exchange with the world around you. You are constantly breathing in the sky and eating the earth. We often think of ourselves as solid statues, carved from permanent stone. But we are more like whirlpools in a fast-flowing river. If you watch a whirlpool, it looks like a single, stable thing. You can point to it and name it. Yet, the water forming the whirlpool is changing every single second. New water enters from upstream, spins for a brief moment, and rushes away downstream. The whirlpool is not the water itself. It is the shape, the pattern of energy that the water takes as it flows through. If the flow of water stops, the whirlpool vanishes, even though the water is still there. In the same way, if the flow of energy and atoms through your body stops, the pattern that is you disappears, even though the atoms remain. In a very similar way, you are a pattern of energy flowing through the emptiness. You are a process, a song being played, rather than the physical instrument itself. The atoms are just the temporary notes. They come together, they dance in a specific rhythm for a few years, and then they disperse back into the wider universe. Your memories, your laughter, your dreams, and your sense of self are not locked inside solid, unchanging gears in your brain. They are preserved in the pattern of the dance itself, even as the dancers are replaced. You are the music, not the strings of the guitar. This realization shifts how we think about identity. We tend to search for ourselves in the material world, trying to find a solid core inside our brains or our chests. We look for a permanent anchor. But when we look closely at the smallest parts of ourselves, we find only empty space and fields of energy. There is no solid center to hold on to. Instead of being a collection of solid pieces, your identity is a dynamic process. It is a continuous wave moving through the ocean of the cosmos. The boundary between you and the rest of the world is a porous screen, constantly whispering to the universe, trading pieces of matter back and forth. Instead of observing the universe from the inside of a solid body, you are the universe itself, swirling in a temporary, beautiful pattern, experiencing itself for a brief moment in time. The silent universe. Have you ever stepped outside on a clear, cold night and simply looked up at the stars? There is a profound, heavy silence that seems to press down from the darkness, a quiet that is deeper than any silence we can find on Earth. It is easy to feel small and fragile when we face that deep, black ocean. We often think of the great empty spaces between the stars as cold, lonely deserts, places where nothing exists and nothing happens. We imagine them as vast stretches of absolute nothingness, separating the tiny, warm islands of light where we live. Yet, this vast emptiness is not a hostile wasteland. It is the very womb of the cosmos. Without these wide, quiet spaces, the stars could not shine, and planets could not orbit. Without the immense distances, gravity could not pull gas and dust together over billions of years to form new worlds. The empty space is the canvas, the quiet partner that allows the dance of matter to happen. It holds the invisible, quiet fields that give everything weight and structure. In a very real way, the emptiness is what makes the existence of everything else possible. It is the background music that allows the melody of life to be heard. We are made of atoms that are themselves almost entirely empty space. The distance between the nucleus of an atom and its swirling electrons is vast, a miniature version of the space between stars. If we squeezed out all the empty space inside the atoms of every single human on Earth, the entire human race would fit inside a single sugar cube. The solid things we touch every day are mostly made of nothing. We are, at our core, woven from the same silence that fills the gaps between galaxies, held together by invisible forces. When we look out into the dark night sky, we are not looking at something separate from us. We are the universe, looking back at itself. The very eyes we use to see the stars are made of ancient stardust, held together by the same forces that govern the deep void. We are a way for the cosmos to know itself, born from the quiet spaces and returning to them. We are not visitors in this empty space. We are a natural part of it. So when you look up at the night sky, do not feel lost in the dark. Find a deep comfort in the quiet. Let the worries and the weight of the day drift away into the vast, spacious reality that surrounds us. We are part of this grand, silent design, suspended in a beautiful, peaceful vacuum. Sleep well, knowing you are safe and at home in the vastness of the quiet cosmos.